everyone. This is the first lecture of week 9. So, until now we have learnt various algorithms to solve unconstrained optimization problem, learnt various algorithms to solve nonlinear program in constrained optimization, right. So, we will now get started with a few algorithms for linear programming problem in constrained optimization, right. So, yeah, linear programming is a special case in constrained optimization problem, and since it is a special case, certain special things can be done, right. So, if you actually look at the chronology of I mean when these algorithms were designed, right. So, you will see that yeah, the algorithm that we are going to see just now, it is called as the simplex method, right. So, this was possibly the first algorithm that was invented for or designed for constrained optimization. All this penalty method and augmented Lagrangian came much later. Okay. So, yeah, simplex method was designed by Danzig, okay, in 1940s. So, it was actually during World War II when he designed this algorithm for yeah, solving a general linear programming problem. Okay. So, before actually going to the algorithm, I will explain in at least in some detail about linear programming problems, its structure, the solution and so on. Okay. So, yeah, let us get started with the general structure of a linear programming problem, right. So, it is of the following form: you will minimize C transpose x subject to A x less than or equal to B and A bar x equal to B bar. Okay. So, yeah, I can write A as a P cross N matrix and A bar as an M cross N matrix. What it means is that the inequality constraints, you have P inequality constraints, right, and M equality constraints. Okay. So, that is exactly what it means, and all those constraints are linear. Okay. So, we will first look at how the feasible set is when we have linear constraints. Okay. So, yeah, I mean this holds even if the objective function is nonlinear. Okay. So, so we are just looking at the constraint set. The constraint set is characterized by linear inequalities and linear equalities, right. So, if a constraint set is characterized only by linear inequalities and linear equalities, okay, how does the constraint set look like? So, we have already seen some examples, right. So, for example, if you had these set of constraints, right, minus x1 plus x2 less than or equal to 0, x1 plus x2 minus 1 less than or equal to 0 and minus x2 less than or equal to 0, right. So, we just saw that this was a triangle, right. So, it was half half and 1 0 and 0 0, right. So, this was the constraint set. So, in this case it actually turns out to be a triangle, right. So, let me I mean give a few more examples, maybe 2 or 3, right. So, let us consider this example: x1 plus x2 minus 1 less than or equal to 0, 2x1 plus 4x2 minus 3 less than or equal to 0 and x1 x2 greater than or equal to 0, or minus x1 less than or equal to 0 minus x2 less than or equal to 0. Okay. So, yeah, I have 4 constraints now, again in 2 dimensions. So, I am giving 2 dimensions because I want you to see how the constraint set looks like. Okay. So, if it is higher dimensions, it is, I mean we cannot visualize it, right. So, that is the reason I am giving in 2 dimensions. So, yeah, x1 and x2. So, if you see x1 plus x2 minus 1 less than or equal to 0. So, the x intercept and y intercept are 1. So, yeah, you will have this, all the points towards the left are part of this particular, that will satisfy this particular constraint. Now, 2 x1 plus 4 x2 minus 3, right. So, the x2 intercept is 3 by 4, which is here, and x1 intercept is 3 by 2, which is here. So, it is this, okay. So, okay, does not look very good, maybe I will draw it in a better manner. Yeah. So, this is maybe I will use different colors if that works. So, the first one x1 plus x2 minus 1 is the red one, okay, and the second one is yellow, which is this, okay. So, the intersection of both, okay, that I will draw in black, okay, it is this and this, okay. So, yeah, so this is going to be 0 comma 3 by 4, right. So, the second constraint, if you put 0 comma 3 by 4, it becomes 0, and this is going to be 1 comma 0, and of course. So, yeah, if we did not have the next two constraints, it will be all of these points. Now, given that x1 is greater than or equal to 0 and x2 is greater than or equal to 0. So, you have only, okay. So, this part, okay, and you can see that this is actually a quadrilateral, right. So, you have it is a 4-sided polygon, if that is better understandable, and the intersection point is actually half comma half. So, that is satisfied by both of these constraints, half plus half minus 1 is 0 and 1 plus 2 minus 3 is equal to 0, right. So, yeah, so you actually get a quadrilateral, right. So, in a similar way I can give more examples where you will actually get 5-sided polygon, yeah, you will call it as pentagon, right, I mean from your high school, right, a 6-sided polygon which is hexagon or any n-sided polygon, right. So, when n is equal to 2, right, that is when you only have x1 and x2, right, you might have any let me call it m-sided polygon, okay. So, the constraint set characterized by linear inequalities and linear equalities are actually m-sided polygons, okay. So, it cannot be anything else, because I mean every constraint is going to be a straight line, right, with possibly different slopes, okay. So, intersection of straight lines will only give you a polygon, right. So, when you have a 2-dimensional problem, the constraint set in a linear programming problem is always a m-sided polygon, it is always a polygon to be precise, okay, fine. So, that is if it is 2-dimensional problem, right. So, what if it is a 3-dimensional problem, when you have x1, x2 and x3, okay. So, in those cases you will actually have something called as a polyhedron, okay. I do not know how many of you are familiar with the term polyhedron, okay. You might have heard of tetrahedrons, right. So, a tetrahedron is something like, so you have a triangle, okay, and on the top, so triangle is in the plane, the xy plane, right. So, on the top there will be a fourth point, okay, it is not in the xy plane, okay. So, I mean it is actually a 4-sided structure, sorry, yeah, where you have 4 vertices, right. So, the 3 vertices are on the plane, xy plane, and there is a 4th vertex on the top. So, if you connect the 4th vertex with all the 3 vertices in the plane, right, so that becomes a tetrahedron, right. So, a tetrahedron is you can say an extension, the 3-dimensional extension of a triangle, okay. So, that is one example of a polyhedron, okay. So, yeah, I mean, I am not going to explain this further because that is not the purpose of the course, but you can search for these terms like tetrahedron, octahedron and so on in Google. I mean, you will see the structure very nicely. Okay. So, what I am saying is that if you have a 3-dimensional LP in a programming problem, right. So, you will see that the constraint set is actually a polyhedron. Yeah, a tetrahedron is a possibility, octahedron is a possibility, or in general a polyhedron. Okay. So, for 2-dimensional LP problems we have polygons, for 3-dimensional LPs we have polyhedrons, for any n-dimensional LPs the term is actually called as a polytope. Okay. Polygon is what we have in 2 dimensions. I mean, that is something that is very familiar to us, like triangle, a quadrilateral, pentagon, hexagon, octagon and all that, right. So, that is a polygon. Similarly, polyhedrons may be one, I mean, some of you might have heard of it, like tetrahedron, octahedron and so on, they are polyhedrons. So, what is the 4-dimensional, 5-dimensional, 100-dimensional, 1885 dimensional extensions of polygon and polyhedron? It is called as a polytope. Okay. So, what I am basically trying to say is that the constraint set characterized by linear inequalities and equalities would be a polytope. Okay. So, fine, I mean, that is nice to know, but why is it relevant? Maybe that is a better question to ask. Okay, let it be polytopes. So, how does it help us? Why is it I mean, does it help us to find the right answer for the linear programming problem? It actually does, because polytopes have vertices, right. So, I mean, you have already imagined or I mean, I have actually drawn polygons here, right. So, the triangle has 3 vertices, right, as you have already seen here, right. Quadrilateral has 4 vertices, and pentagon has 5 vertices, octagon has 8 vertices and so on. And just a few minutes back I mentioned that a tetrahedron has 4 vertices, right. So, the 3 vertices in the xy plane, the triangle, and there is a 4th vertex on the top, right. So, there are 4 vertices for a tetrahedron. Okay. Similarly, in a polytope you will have some number of vertices, okay, and I claim that the solution of a linear programming problem is always a vertex. Okay. So, that is why the polytope result is interesting. Okay. So, let me actually write down that result. Okay. So, I will write it as a claim, I mean, because it can be proven. Okay. Claim is that the solution of an LP is always a vertex of the polytope. Okay. So, you should now ask why that is the case, right. So, yeah, why can we not have some other point as the solution? So, for example, if you see this constraint set what we had here, right. So, what we are saying is that you can give any C transpose X. Okay. So, yeah, this is something to be noted. The claim says that I have not mentioned anything about C transpose X, right. So, what we are saying is that if the constraint set is what is given here, let us say minus x1 plus x2 less than or equal to 0, x1 plus x2 minus 1 less than or equal to 0, minus x2 less than or equal to 0, right. So, this is a triangle with 3 vertices, right. So, whatever be your C transpose X, the solution is either 0, 0, 1, 0 or half comma half, it is one of these three, okay, it is never anything else. Okay. So, I do not know if I mean of course that is that is an exciting result, right, because yeah, the C transpose x can be anything, I mean C1 x1 plus C2 x2, right, C1 C2 can be anything, it can be 5 and 10, it can be minus 5.7 and minus 14.8 or 199.9876 and minus 1194.78457, right, whatever it is, it can be the C1 and C2 can be anything. The answer for, I mean if the constraint set is given by this triangle whatever you have here, right, so it is going to be either 0, 0, 1, 0 or half comma half. Okay. So that is what this claim means, okay, in the if you take this particular example. Okay. So why is that the case? So let us prove this. So suppose not, okay. So then the solution x star can be written as x star equal to say x dash plus x double dash by 2, right. So suppose if it is not a vertex, say for example it is a point here, okay, then yeah, so where x dash x double dash belongs to the feasible set, that is the polytope. Okay. So for example if yeah, x star is the solution that is here, okay, in the line instead of the vertex, right. So I can write it as the midpoint of this and this, right. Similarly if you are taking a point here, I can write it as the midpoint of two closer points, right. So I can always do that, right. So that is but if it is a vertex I cannot do that. So if it is a vertex, I mean how can I write it as the midpoint of two such points, right, that is if I can write it that way then it is not a vertex, right. So yeah, fine, the solution can be written this way. Suppose yeah, so the solution x star is a solution because C transpose x star is the minimum among the feasible set, right. So then we have C transpose x star equal to C transpose x dash by 2 plus C transpose x double dash by 2. Okay. So but this is not possible because x dash and x double dash are not the minimizers, right. So that means, so yeah, if x star is the solution, right, if x star is the solution, then C transpose x star is less than or equal to C transpose x dash and C transpose x star is less than or equal to C transpose x double dash. Okay. So yeah, or I can write C transpose x dash greater than or equal to C transpose x star and so on. Okay. So I mean substituting that back here, you will have this is greater than, I mean C transpose x dash is greater than or equal to C transpose x star. So that is C transpose x star by 2 plus this again is C transpose x star by 2, which is C transpose x star. So this is possible only if C transpose x dash equal to C transpose x star and C transpose x double dash equal to C transpose x star, right. So possible only when C transpose x star equal to C transpose x dash equal to C transpose x double dash. Okay. So yeah, if x star is the unique minimum, this is not going to happen, but if x star is one of the minimizers, then it can happen that yeah, there are more number of points I mean that are minimizers, right. So, what that means is that you either have a vertex as the feasible set, right, or you have all of this line as either has the vertex as the solution, or you have all of the points in this line as the solution, right. So, what that means is that at least there is one vertex which is always a solution. Okay. So, maybe I should have written this claim a little, I mean I can correct this claim as follows. So, yeah, a vertex of the polytope of the feasible set, you can say feasible polytope, is always one of the solutions. Of an LP. Okay. So, what this tells us is that if it turns out that C transpose X star equal to C transpose X dash equal to C transpose X double dash. Okay. So, you can kind of extend it to I mean throughout the line or throughout the plane, line if it is 2 dimensional and plane if it is n dimensional, right. So, thus the solution can be extended up to one of the vertices. Okay. I think that is the proof. So, if this does not happen, I mean C transpose X star equal to C transpose X dash equal to C transpose X double dash, we have a contradiction already, right. Either this is not the solution or it is a vertex, right. So, if it is equal, then you can actually extend it up to the vertex, right. So, fine. So, the good part about this claim, whatever I have proved here, is that we can stop by searching the vertices, right. So, given a linear programming problem, we do not have to search every point. Okay. It is sufficient if we search for the vertices of search on the vertices, right. So, whichever vertex gives us the minimum value of the objective function, that will actually be the solution of the linear programming problem. Okay. All right. So, fine. Now we have another question to ask. Given a particular problem, how do we actually find the vertices, right. So, of course, if it is 2 dimensional, we can actually try to plot the polytope ourselves, right. I mean try to draw the polytope ourselves and find what the answer is. What can we do for higher dimensional problems? Say if it is 3 dimension, maybe we can try to some extent, but if it is 4 dimensions, then geometry option is closed, right. So, and if it is 10 dimensions, 15 dimensions, forget about it. I mean in today's scenario, we have problems which are of very high dimensions, 1000 dimensions and so on, right. So, in that case, I mean drawing the picture and finding what a vertex is simply impossible, right. So, we want to tell the computer that these are the vertices somehow. Okay. How do we do that? Okay. So, I am going to explain how Danzig's simplex method does it. Okay. So, I mean if you people have not got the name already, okay, so it is Danzig. Okay. So, this is the name of the person who proposed the simplex method. Okay. So, what does he do? He does the following. So, he first starts, so I told you that yeah, this is the problem, the general structure of the linear programming problem that we have, right. So, he first proposes to convert this to the following form. So, maybe I will write it as a dash, because I mean the a and this a could be different, okay, and x greater than or equal to 0, okay, in such a way that, okay, a dash is an m cross n matrix with rank of A equal to m, okay. So, this is important, okay. So, the first thing that we have to do is, when you are given a particular problem, particular linear programming problem, there are many ways of representing a particular linear programming problem. Mathematically, all of them could be the same, right. So, since we need to find the vertex mathematically, okay, so that is very important, because geometrically is, I mean, it is not possible when the dimensions are very high, right. So, we have to find them mathematically. So, for that, the first thing that he proposes is convert this problem, minimize C transpose x subject to A x less than or equal to b, a bar x less than or equal to b bar, as this particular form, okay. What it means is that you should have only equality constraints, okay, and inequality constraints are very specific. It has to be x non-negative, okay. No other kind of inequalities are accepted. You have to have x non-negative as the set of inequality constraints. I mean, that's that cannot be compromised, and you should not have any other inequality constraints. Keep that in mind, okay. And of course, you can have equality constraints. You should convert the form that you have at the left to the form that you have at the right, okay. So, how to do this? I mean, that is the first step in the simplex method. We will see it in the next lecture.